So, welcome friends to this session of our discussion, and in this session we will discuss the analytical solution of the matrix difference Riccati equation. The expression for the matrix difference Riccati equation we have developed in the previous class. We have seen the two forms, and objective is to determine the value of the P. If P k is known to me, I can find out the LA k, and this LA is nothing but my Kalman gain, which I can utilize along with the state feedback to get my optimal control U. So, and in analytical solution of the matrix difference Riccati equation, it determines the transient and the steady state solution of the matrix difference Riccati equation. This method involves the calculation of eigenvalues and eigenvectors. As we have determined this for a continuous time systems, in the similar manner we can we can find out the value of the P using the eigenvalues and the eigenvectors. But there my system was the continuous, but here the system will be the discrete in nature. Now, the Hamiltonian system with state and the co-state equation, as you know, we have developed the Hamiltonian system in terms of the x k plus 1 and lambda k, which was nothing but my A k minus E k Q k A transpose k x k and lambda k plus 1. But in this case I have to find this in terms of the x k lambda k. So, this means this equation I want in terms of the x k. We have derived that our Hamiltonian system we can represent as x of k plus 1, lambda of k as a k minus e k q k a prime k x k lambda k plus 1, where e k is b r inverse b prime. So, now this set we have to convert in terms of the x k and lambda k. So, if we write the first equation, this is x of k plus 1 as a k x k minus e k lambda k plus 1. My objective is to represent this in terms of the x k. So, I can write a k x k as x of k plus 1 plus e k lambda of k plus 1, or simply I can write my equation as x k equal to A inverse x of k plus 1, I am pre-multiplying this with A inverse. So, this is A inverse k E k lambda k plus 1. So, now this x k I have represented in terms of the x of k plus 1, lambda of k plus 1. Similarly, the second equation which already given me in terms of the lambda k, but this is q k x of k plus A transpose k lambda k plus 1. So, this lambda k I have to represent in terms of x of k plus 1, lambda of k plus 1. This is already the lambda of k plus 1. So, I can substitute this x k at this place. So, what I will get? Q k A inverse k x of k plus 1 plus A inverse k E k lambda of k plus 1 and plus A transpose k lambda of k plus 1. So, if I will expand this, this is nothing but my q k A inverse x of k plus 1 and this I can include into this A inverse k E k plus A transpose lambda k plus 1. So, from these two equations, one is and second is, I can write the my required form as x k lambda k. So, what is my x k? A inverse of k x of k plus 1, A inverse of k lambda of k plus 1. So, in this, just for writing purpose, the k has been dropped out, but this is A k inverse E k, this is q k A inverse k A transpose of k q k A inverse of k E k and lambda k plus 1. So, here A transpose we are writing as A prime. So, by this I can write my Hamiltonian system which we have derived in this form as x k plus 1 lambda k in terms of the x k lambda k, and this we will take as my matrix H. And we also know for the closed loop LQR gain we determine using the transformation as lambda k equal to p k x k, this already we have seen, and the matrix difference Riccati equation is A transpose p k plus 1 I plus B R inverse B transpose p k plus 1 inverse plus multiplied with A plus Q. This is my matrix difference Riccati equation which we have derived in the previous lecture, and with my boundary condition as p k f equal to f of k f. Here my objective is to find out this p k using some analytical approach. So, to determine this p k, I consider my matrix H. So, this matrix which we have written here giving the relation between x k lambda k to the x k plus 1 lambda k plus 1. So, this is A inverse E, Q A inverse A transpose Q A inverse E, we are taking as my matrix H. Now, consider a transformation matrix which we are taking as a J, which is 0 0, the diagonal element is 0 and the off diagonal elements are the unity matrix. So, the size of my matrix H is 2n by 2n, because this will have the vector lambda x k and lambda k. I have the n cross 1 states as my x and n number of the lambda values. So, total size of the matrix H is 2n by 2n. So, I have to consider the J matrix also by 2 by n by 2n. So, this 0 is nothing but representing a null matrix of n by n, this is representing a null matrix of n by n, and I representing a identity matrix of n by n. So, I have the total 2n rows and the 2n columns given here. So, if I will take the inverse of the j this, so naturally I can very easily prove this is nothing but equal to minus of j. Minus of j means only these two elements will interchange their sign. So, I have j inverse as minus j. So, I can easily prove further H transpose J H is nothing but equal to j, which is given here. We have the H transpose means what the H matrix we got here, we are taking the transpose of this matrix. So, what is the transpose of this matrix? So, we are taking the matrix H as A inverse E, I am dropping the K again, A inverse E, Q A inverse, this is A transpose plus Q A inverse E. I have to take the transpose of this matrix. So, what will be this? My first element hoga is A inverse transpose, then Q A inverse transpose, A inverse E transpose, because this element will come here, all the elements, and A transpose plus Q A inverse the transpose of the whole. So, what the first element I will get as my, we are proving this H prime A minus transpose, because this is I am writing as A minus T. So, this is A minus T means transpose of the A inverse matrix. So, we are taking the A inverse and then taking the transpose. I will write this, this is transpose of the A inverse, Q transpose, Q we have taken as a symmetric positive semi definite matrix, because this is symmetric. So, I can take this as the my A minus transpose Q. This term, this E is B transpose, sorry, B R inverse B transpose. If I will take the transpose of this, so this is B R inverse B trans, its transpose is this remains same, and this will be B. So, this is again E inverse of the A transpose. If I will expand this, A transpose will be A plus E remain the E, A e to the power minus T, and Q remain the Q. So, I get this matrix e to the power, sorry, inverse of the A transpose, inverse of the A transpose multiplied with Q, E multiplied with inverse of the A transpose, A plus E to the power minus T Q. So, I am getting this as my H transpose multiplied with J. So, I am trying to find H prime J H, H prime J H, you multiply this. So, we will get the same matrix as we are getting the J. So, this means H prime J H we have taken as the J. We are post multiplying this H inverse. So, if I will multiply this H inverse, so this is J H inverse is H prime J. So, and this, say I will write here post multiply with H inverse. Now, here pre multiply with J inverse. So, what we will get? J inverse H prime H transpose J as J inverse J H inverse. This is nothing but my I. So, I can write my H inverse as J inverse is minus J H prime J. So, I can easily find out the inverse of the H if I have the transformation J multiply with the H prime and multiply with J. So, I can have my inverse of matrix H, which is this matrix here, its inverse is nothing but J H prime J. So, H inverse simply by taking the value of the J H transpose and J, I will get the inverse of matrix H. Why we need this matrix? This will be clear just now. Now, as we said earlier, this analytical approach is based on the eigenvalue and the eigenvector approach. We consider V to be the eigenvector of matrix H. This means my eigenvector identity HV equal to mu V will exist, where mu will be the eigenvalue of matrix H. Then this is my H V1 V2, which is the structure of the V I have considered. V is my eigenvector corresponding to the eigenvalue mu. We have the equation HV equal to mu V. This has to be satisfied if V is the eigenvector of mu. We are writing this H multiplied with the V as mu V1 V2. In the next step, you can follow yourself. We are rewriting the same equation in a different form. How? We are writing this as V2 minus V1. So, V2 remain the same. So, this by writing the equation independently, then I can rearrange the whole equation as A transpose plus Q A inverse E minus Q A inverse E A inverse V2 V1. Here also V2 V1. Now, if you will see what is this matrix? This matrix is same as my H transpose matrix. So, this matrix is nothing but the inverse of my H transpose. So, this is my H inverse matrix. If I will take the transpose of the H inverse, so we determine the H inverse as A plus transpose of the A inverse Q, my next element is minus E A to the power minus T next is minus A to the power minus T Q and my last term is A minus T. So, this is the H inverse which we have determined using the minus J H prime J. What we are trying to find out, what is this matrix? If I will take the transpose of this matrix, this means transpose of the H inverse, which I am writing as H to the power minus T. So, what will be the transpose? Transpose of the first element. If I will transpose this, this will be A transpose plus Q transpose, remain the Q, transpose of the A to the power minus T is inverse of the A transpose. So, this is again I will transpose nothing but the A inverse, E remain the same. Similarly, here I will write this is A inverse E. If I will write Q remain the same minus Q A inverse, and this is A inverse. And by rearranging this V1, V2 and V1, I am getting A transpose plus Q A inverse E minus Q A inverse. Sorry, I did a mistake because we are transposing this. So, these two terms will interchange. So, my in this terms say we are transposing. So, I will get the first term is this in the first row, my second element will be the transpose of minus A T A to the power minus T Q, which will be minus Q A inverse, and this term will be nothing but the transpose of this term, and the transpose of this term is A inverse E, and this remain the same. So, my second term is minus Q A inverse, this is minus A inverse E A inverse. So, this is nothing but my inverse of the H transpose. So, I am getting this as transpose of the H inverse multiplied V2 minus V1 mu V2 minus V1. So, what is the meaning of this? So, this means if I will consider this is the eigenvector corresponding to the eigenvalue mu. So, what I can say? Mu is the eigenvalue of inverse of the H transpose, and corresponding to mu eigenvalue, my eigenvector is V2 minus V1. So, mu is the eigenvalue of H to the power minus T, means this is the transpose of the H inverse. This means mu is also the eigenvalue of H inverse, because if a matrix have the eigenvalue, its transpose will also have the same eigenvalues. So, what the eigenvalues of the H inverse? The same eigenvalues of the transpose of the H inverse will have. So, mu is the eigenvalue of H inverse and the transpose of the H inverse and the H inverse. So, if mu is one eigenvalue of the H inverse, this means one upon mu is the eigenvalue of H. So, by this observation we can say that if mu is the eigenvalue of H, 1 upon mu is also an eigenvalue of H. So, we can say if mu is an eigenvalue of the Hamiltonian matrix H, then 1 upon mu is also an eigenvalue of the Hamiltonian matrix H. What is the significance of this? Say we are my Hamiltonian matrix, the Hamiltonian matrix is a discrete matrix. So, if eigenvalues which lie inside the unit circle, that are my stable eigenvalues, and the eigenvalues which lie outside the unit circle, this means those eigenvalues are my unstable eigenvalues. So, if mu is less than 1, I have stable eigenvalues, and if so 1 upon mu, which naturally will be greater than 1, means unstable eigenvalues. So, this means my matrix H will have a set of stable eigenvalues and a set of unstable eigenvalues. So, this property of my Hamiltonian matrix, due to this property we can convert my Hamiltonian matrix into the diagonal form such that it will have one set of the eigenvalues and the another set of the eigenvalues. So, one set is the m, let us say the mu, and m inverse, let us say the 1 upon mu. So, I can diagonalize the Hamiltonian matrix in such a way that it will have all eigenvalues which are less than 1 or inside the unit circle as a one set, and the another set the eigenvalues which are outside the unit circle or greater than 1, they all can be placed in the diagonal form. So, I stop my discussion here for this, and in the next class we will continue to find out the final value of the P in terms of the its eigenvalue and the eigenvector analysis as we are doing. Thank you very much.